our next speaker, who is Zephyr. So we'll just kick you off, Davey. There we go.
Hello?
Hello.
Hi.
How are you doing?
I'm doing fine.
That's fantastic. Are you ready to go?
Yep, I'm ready to go.
You look ready.
Yeah, all right. Well, my name is Zephyr D Benton, and I am a senior at the University of Toledo studying accounting and minoring in finance. And my research topic is over how to finance a space mining operation on the moon and near-Earth asteroids. So what do I mean by when I say financing a space mining operation? Well, the main problem right now is that space mining requires a large amount of upfront capital for a sustained period of time. Now, our current financial methods cannot accommodate such a large endeavor. So what my research is, that's where my research comes in. My research is divided into two parts. The first part is I am researching currently proposed alternative investment vehicles to finance a space mining operation. A lot of my research is focusing in on rare earth metals mining, which also requires a large amount of upfront capital for sustained periods of time. The second part of my research is I am proposing the creation of a series of space mining tax credits, which will be similar to Canada's mining tax credit and renewable energy tax credits. These tax credits will give investors who invest in space mining operations much more immediate returns on their investments, and it will make space mining much more of an attractive investment. A reason this is important is that we need to establish space mining in order to tap into the space economy. If we don't have a vibrant space economy, we're not going to be able to do cool things such as space manufacturing and fund deep space exploration. Thank you for listening to my presentation.
Thank you so much, Zephyr. That was also really fantastic. We definitely need more people who are in finance and are good with money in the space industry to help us build all these projects that we're dreaming of. So it's a fantastic presentation. Thank you so much. We have Ilhan next. So seems like Ilhan is not here at the moment. Oh, no, here he is. Okay, fantastic. Great to see you.
Can you hear me?
Yeah, definitely.
How's my audio quality?
Your audio sounds good.
All right, great. I'm going to share my screen right now.
All right, fantastic. I'll just get off here so you can present.
Oops, that's the wrong screen. My apologies. All right, this should be right. All right. Hey, everyone. Good afternoon. I'm here for the next 3 minutes, and I'm going to talk about bio-inspired ceramic shielding for a spacecraft. The first question some of you may have is why ceramics? Traditional shielding for impact for spacecrafts is usually from metals or composites. The ceramic has a host of properties that makes it attractive. Firstly is the high thermal stability. The high melting point and the insulative properties of ceramics ensures that for extreme conditions of space, especially with launch and re-entry, ceramics can sustain those loads. Low density means weight savings. Significant mechanical properties, such as high stiffness and high compressive strength, make it an attractive candidate for shielding applications as well. However, and this is the reason why ceramics aren't widely used, is the brittle and low toughness nature. So how do we toughen ceramics? We're going to look at one of the most experienced designers that we know, and that's nature. On the screen, I have a picture of nacre, more commonly known as mother of pearl. This structure is made from calcium carbonate, which is a ceramic, surrounded by a soft organic material. What this ensures is that stiffness mechanisms are generated through the hard ceramic, and toughness is generated through the soft, elastic, organic interface. In fact, nacre has higher toughness and combined toughening mechanisms compared to monolithic ceramic structures. And how do we produce this? We use a high energy laser, and we cut the ceramic samples at specific architectures to mimic the structures in nature. What we do is we then layer it with a ceramic as well as a polymer. The polymer is Serlin, and then we put it under impact testing using 3 impactors. Here are 2 examples of the structures we can make. We've done a hexagonal, perfectly ordered architecture, a honeycomb structure, and we also have a more interesting structure, which is a pseudo-random generated architecture. We actually have a method to produce randomness and associate designs with randomness. This is more commonly found in nature. Here are some results using digital image correlation. Essentially, what this shows is that for a plain ceramic, you can see cracks propagate in a linear fashion to the edge of the samples. However, when we architecture these samples, we're actually disrupting the crack propagation, which is inducing a toughness mechanism, making these ceramics tougher. Finally, the impact results themselves. We have energy absorption on the left side, and architectured ceramics, and baseline plain ceramic samples. You can see that with the second and third impact, we're actually decreasing the energy absorption of a simple basic ceramic. However, when we add these patterns and we use these polymers, we're actually increasing the energy absorption, so much so that there's a 220% increase in toughness. Thank you all for your time.